In this video, we're talking about a very specific case of compound interest. I mentioned in the intro to compound interest video that the more often interest is compounded, the more interest you will earn if you've deposited money. So if interest is compounded monthly, you would earn more than if it were compounded yearly or annually. If it were compounded daily, you'd earn more than if it were compounded monthly. If it were compounded hourly, you'd earn more than if it were compounded daily. And if it were compounded every second, you'd earn still more. However, that value doesn't increase forever. There's a limit to that value. And what we now understand is that that limit it relates to the constant E, which is Euler's constant. And E is used in various things, in various applications. One application for E is in continuous compound interest. And this is the idea that if interest were compounded continually, like every microsecond, that is what E approximates in this formula that we're going to see. In practice, most banks today don't offer continuous compound interest. And in fact, many books give it less attention than it got, say, 40 years ago or even 20 years ago, because it's kind of just a novelty. The difference between something that's compounded, say, daily and something that's compounded continuously is not a big difference. Even with large amounts of money, the difference as a percentage of the total amount is negligible. So continuous compounded interest isn't used a lot. When it is, there's a special formula, and that special formula is listed here. There's kind of some shortcut ways to use this on your calculator using TVM Solver. I'm not going to talk about those ways because they're really more effort than they're worth. For the few problems you have with compound interest, just use this formula. It's very straightforward. And this is an example where actually most books give the same formula. I know I mentioned in the previous video that different textbooks give different formulas for compound interest, but pretty much everything uses the same formula for continuous compound interest. And it's PERT. A equals PERT. It is the principal times this constant E, and E is an irrational number. Think of E, it's a lot like pi. It's a different value, but it's similar in that we just use this letter E to stand for this one particular constant, Euler's constant. And it's pronounced Euler. Usually, sometimes people pronounce it Euler, but it's spelled E-U-L-E-R. It was a mathematician. And then we take that to the interest rate as a decimal times t, the number of years. So let's look at an example. Suppose that $5,000 is invested at an annual interest rate of 3.1% compounded continuously for 4 years. Find the compound amount. Compound amount is just what they're doing when they say find how much you'll have at the end of 4 years. That's all we're talking about here. So our formula is going to be A equals P times E to the RT. And it's important that we remember we do exponents first. And so this is not e to the r and then times t. It's e to this value together, e to the r times t. So here we're going to have A equals $5,000 times E, and it's going to be to the 0.031 times 4. And now that I have this written out like this, I can put this in my calculator. So we'll just make this a little bit bigger so it's a little easier to see. Now, for this to work, you're going to need a calculator that does have an E key somewhere on it. If you don't, you can approximate E, but your answer might be wrong. Let me show you what E is. So E is approximately 2.718281828. So if you don't have an E key on your calculator, you can use this in this formula. You could replace E. That was not what I wanted to happen. Whatever just happened there. There we go. You could replace E and say that that's going to be approximately 2.718281828. That's only an approximation. E is irrational. It goes on forever. And it's important that you not, if you do this, don't round it. Don't say, oh, it's about 2.72. If you do that, your answer is not going to be accurate enough. If you keep it to a whole bunch of decimal places, you have a better shot of your answer being accurate. But hopefully your calculator has an E key on it. If you're using MyMathLab for problems, the calculator in MyMathLab when you're doing compound interest should have an E key on it. Now, normally E is not just to itself like it is here on the TI. And that's true for the TI as well. If you look over on the left-hand side of the calculator, you're going to see a key that says LN. And LN, let me see if I can, ooh, that wasn't what I wanted at all. Yeah. See if I can get to my commands here. Yeah, oh well. LN stands for the natural log. We aren't going to worry about that in this course. Sometimes in finite we do talk about this because there's a way to find any of these values. We're just going to solve for A or P. But you could solve an equation like this for R or for T. If you do it, you have to use logarithms. The natural log and E are related to each other. We aren't going to get into that. To work with logarithms well, you really need college algebra first, I think. And college algebra isn't a prerequisite for this class, so that's one of the reasons we aren't doing that. But we can certainly use just our regular E to the X key, and that's what you get when you hit on the TI, the second key and natural log. And what you'll see is E, and then there's a spot for you to put the exponent. So let's make this screen a little bit bigger. Just so it's a little easier to see. There. So you see here I have E, and then I have this flashing part in my exponent. And so that's where I'll put in 0.031 times 4. In fact, I'll just do that this way. I'll do it this way first, and then I'll do the other way we can do it. So 0.031 times 4. And I'm going to hit enter, and I get this. And then I'm going to multiply that by 5,000. And so I will see that after 4 years' time, I'm going to have in my account $5,660.08. So I can also just type this in order. So I could type it in like this. I could type in 5,000 E, and the calculator will know that it's times E. You could also put the times sign in there. I often will do that. And 0.031 times 4. Now I'll get the same answer. Again, if you have a scientific calculator, your calculator might not be able to multiply in an exponent for you. And so in a case like that, I would multiply that out first. I would do first 0.031 times 4 and see that equals 0.124. And so if I had a scientific calculator, my work might look more like this. 5,000 times E to the 0.124. And I'm going to get the same answer. So that is compound interest, continuous compound interest, kind of in a nutshell. It's just this one formula, P times E to the RT. And as long as you remember to multiply R times T first and then raise E to that product and then multiply your answer by P, continuous compound interest should work out very well. Let's just do one more. We'll do a sample problem using this here in a second. I'm going to pause and resume. So I have here just some figures I just randomly came up with. So let's say I have $843.52. We usually use round numbers, but there's no need to. I have this much, I've saved this much money. I found a super good savings account, which would be awesome if they paid this much. And it pays 7.05% interest, and it's compounded continuously. And so I put my money into this savings account and I forget about it for 6 years. And in 6 years' time, my bank sends me an email and says, "Hey, Carl, you have money in your account. Are you ever going to withdraw that? Because it's kind of inactive right now. You better do something." And I think to myself, I wonder how much is in that account. How do I know? Well, I can figure this out with my fun continuous compounding formula. That A equals PERT. Make this a little bit thicker. There we go. P to the E to the RT. So what do I know here? I know my present value is $843.52. And again, when we say present value, that always means our beginning value, our starting value. So even if I'm figuring this out 6 years in the future, what I do is I look back at what did I start with. That's what I consider my present value. My interest rate is 0.0705. That's 7.05%. And my time here is 6 years. So I'm going to put in the calculator 843.52 times e to the 0.0705 times 6. So let's do that. So $843.52. I'll put a time sign in here. Okay, and you'll do that if you have a scientific calculator. Times e to the x. That is this key over here again on the right-hand side of my screen. Sorry, on the left-hand side of my calculator. It's shift key and the natural log on the TI 83 or 84. The natural log is what the LN key is. That stands for natural log. Other scientific calculators and other graphing calculators also have E keys on them usually. Sometimes they're hidden away in a menu. So you're going to have to dig to get it. But it should be on there. One thing you can do if you don't have an 83 or 84 is just Google your calculator's manual or look on YouTube or some other site. I say Google and YouTube. Use obviously whatever sites you want for those things. And find your manual or find how to get the E key on your particular type of calculator. Other common types like Casios and HPs and stuff like that also have E keys on them. They're just in different spots usually. And so it's going to be e to the 0.0705 times 6. And so after 6 years, I should have in my account about $1,287.66 if my interest were compounded continuously. Let's actually do one more thing. Let's compare that. Let's compare this continuous compounding to if my interest were compounded quarterly instead. So let's compare. Let's say that I was comparing two banks, and one was compounded quarterly and one was compounded continuously. So my quarterly interest is going to be A equals P times 1 plus I to the n, where I is the interest rate over M, where M is the number of times it's compounded a year. And so plugging in my values here, I would get, again, we're saying that it's compounded quarterly, $843.52 times 1 plus 0.0705 over 4. And then quarterly for 6 years, that would be 4 times 6, or 24. So let's plug that in. And again, on the TI-84, you can use TVM Solver for this because it's regular compound interest. But I'll just put it in as the formula. So if it were compounded quarterly, at the end of 6 years, I would have $1,282.93. So there is a difference, right? There is just under a $5 difference between continuous compounding and quarterly compounding. That difference would get smaller if we figured out if it were compounded daily, there would be a much smaller difference. If it were compounded monthly, it would also be a smaller difference. So you need to be able to find continuously compounded interest. This is one of the problems that will show up on your final exam. I will say on your final exam, there is a page of problems that are all about interest, and it's going to be a problem kind of like this. It's a nicer value, like it's a nice round value, like $1,200 or something, and it's a different, it's an easier value for interest, like 5.2% or something like that. But it's going to ask you, what would this be if interest were simple interest? What would it be if it were compound interest compounded annually, semi-annually, quarterly, monthly, weekly, and continuously? So for your final exam, you need to know the compound interest formula, you need to know the simple interest formula, and you need to know the continuous compound interest formula. So you have to be able to use those for your final exam. If you have any questions about any of them, please let me know. Good luck as you move forward.